Somewhere around 400 million years ago, while dinosaurs were already roaming across Earth, two moons orbiting Saturn may have slammed into each other in a collision so violent that it reshaped the entire Saturnian system. For centuries, scientists assumed Saturn's rings had been there almost as long as Saturn itself, ancient leftovers from the birth of the solar system. But observations from the Cassini spacecraft completely changed that picture. The rings appeared to be remarkably young, likely forming sometime within the last few 100 million years. That means they may have appeared long after dinosaurs were already walking across Earth. And that created a huge mystery. If Saturn's rings weren't primordial leftovers, where did they come from? A new study published in February offers a fascinating possible answer: a chain reaction of orbital chaos, moon collisions, gravitational resonances, and destruction that may have unfolded across hundreds of millions of years. And at the center of the story is Saturn's largest moon, Titan. To understand why this is so important, we have to go back to the very beginning of humanity's observations of Saturn. When Galileo Galilei first pointed his telescope towards Saturn in 1610, he was completely baffled by what he saw. Saturn appeared to have two enormous objects sitting beside it, almost like ears. A few years later, those strange objects seemed to disappear. Then they returned as strange arms or handles extending from the planet. Galileo wasn't actually seeing moons at all. He was seeing Saturn's rings. Because Saturn's axis is tilted by roughly 27 degrees, the angle at which we see its rings changes over time. When the rings turned almost perfectly edge-on toward Earth, Galileo's primitive telescope simply couldn't resolve them. It wasn't until 1659 that Dutch astronomer Christiaan Huygens correctly realized that Saturn was surrounded by a continuous ring system. During the same period, Huygens also discovered Titan. As telescopes improved, astronomers began uncovering just how complicated Saturn's neighborhood really was. Giovanni Domenico Cassini discovered several additional moons and, in 1675, identified a major gap within the rings that eventually became known as the Cassini division. Then, during the 19th century, astronomers discovered something even more surprising. Saturn's rings weren't solid structures. They were made of countless individual particles orbiting Saturn independently. The true complexity of the rings became even clearer when spacecraft finally reached Saturn. Pioneer 11 and the Voyager probes revealed structures that telescopes from Earth could never have seen. Voyager 2's 1981 flyby showed that the major rings were themselves divided into enormous numbers of smaller ringlets. Then came Cassini. For more than a decade, Cassini orbited Saturn, passing between the rings, studying the moons, and eventually diving repeatedly into the narrow region between Saturn and its innermost ring. The mission completely transformed our understanding of the Saturn system. The rings are incredibly thin, despite stretching hundreds of thousands of kilometers across. Their particles are overwhelmingly composed of water ice, ranging from tiny grains to much larger chunks. And their total mass is surprisingly small compared with the spectacular structure they create. That led scientists to another important clue. Space dust and micrometeorite impacts should gradually contaminate and darken exposed ice. So if Saturn's rings had really existed for billions of years, why were they still so bright and clean? Their low mass also meant scientists could estimate how quickly this contamination should accumulate. The result was startling. The rings appeared to be far younger than Saturn itself. Instead of being billions of years old, they may have formed sometime around tens to hundreds of millions of years ago, depending on the assumptions used. That means Saturn's rings could actually be a relatively recent feature of the solar system. So scientists had to ask the obvious question. What could create an enormous ring system around a planet hundreds of millions of years after that planet formed? One possible mechanism has been understood for more than a century. A moon traveling too close to a giant planet can encounter enormous tidal forces. If those forces become stronger than the moon's own gravitational cohesion, the moon can be torn apart. Its debris can then spread along its orbital path, potentially creating a rain. This critical distance is known as the Roche limit. Saturn's system contains plenty of evidence that gravitational destruction has happened before. But in 2022, researchers from MIT proposed a particularly interesting scenario. They suggested Saturn once had another moon, nicknamed Chrysalis, orbiting between Iapetus and Titan. According to the idea, interactions with Titan gradually destabilized Chrysalis's orbit. Eventually, the moon moved into a dangerous region around Saturn and was destroyed, leaving behind debris that eventually became the rains. But later simulations suggested a problem. Chrysalis may have been more likely to collide with Titan than to approach Saturn closely enough to be torn apart. And that created an even bigger mystery. Because when researchers simulated the system, another moon kept getting thrown out. Hyperion. Hyperion is one of Saturn's strangest moons. It is irregularly shaped, extremely low density, and rotates chaotically rather than maintaining a simple predictable orientation. Yet Hyperion is still here today. Even more interestingly, its orbit has a special relationship with Titan. That relationship may be a clue to what happened hundreds of millions of years ago. Researchers realized that Hyperion's strange orbital history might not be an unrelated coincidence. It could be part of the same ancient catastrophe. Instead of imagining the Saturn system as a collection of independent moons, the researchers began treating it as one interconnected gravitational machine. That changed everything. Their simulations suggested that Titan may once have collided with a much larger moon, a body described as a possible precursor to Hyperion. The hypothetical object has been referred to as Proto-Hyperion. In the simulations, Proto-Hyperion and an earlier version of Titan repeatedly interacted through gravitational resonance. In some simulations, the two bodies eventually collided. And when the researchers ran dozens of different scenarios, collisions occurred in a significant portion of them. The best fit scenario places the event roughly 400 million years ago. So what would have happened? Before the collision, Titan may have been smaller and moving in a more circular orbit around Saturn. A change in Saturn's broader gravitational configuration could have destabilized Proto-Hyperion's orbit. The Moon then entered a powerful 2-to-1 orbital resonance with Titan. That means for every orbit Titan completed, Proto-Hyperion completed too. Repeated gravitational interactions can amplify tiny disturbances over time. Instead of simply passing each other, the two moons would repeatedly tug on one another in the same orbital configuration. Eventually, the system became unstable. Proto-Hyperion moved inward. Its orbit became increasingly dangerous. And eventually, the two moons collided. The impact would have been catastrophic. Titan could have absorbed a huge portion of the smaller moon's material, while other fragments were scattered throughout the Saturnian system. Some of that material may have eventually formed the irregular moon Hyperion. That could help explain Hyperion's strange shape, low density, young apparent age, and chaotic rotation. The collision may also explain another major mystery. Iapetus. This distant moon has an unusually tilted orbit, and its history has long been difficult to explain. The researchers' simulations suggest that the same gravitational chaos generated during the ancient Titan collision could have altered Iapetus's orbital path. But the consequences may not have stopped with the moons. Titan itself could have been pushed into a more eccentric orbit. And even today, Titan is slowly moving away from Saturn. Cassini measurements revealed that Titan's outward migration is faster than older models had predicted, at roughly 11 centimeters per year. That unexpectedly rapid migration provides another piece of the puzzle. As Titan gradually moves outward, its changing gravitational influence can interact with other moons and with Saturn's own rotational dynamics. And this may connect directly to one of Saturn's strangest features: its enormous axial tilt. Saturn is tilted by roughly 27 degrees. For decades, scientists have debated how the planet ended up in such an unusual orientation. The new model proposes that Titan's orbital evolution may have played a major role. As Titan migrated outward, its changing orbit altered Saturn's precession, the slow wobbling of the planet's rotational axis, similar to the wobble of a spinning top.